Okay, so in this video I'm going to look at a few more problems from chapter 20. I'll start with problem 19. So here we have a Carnot cycle shown in the figure. It has the following conditions. The volume at A and volume at B is given. The higher temperature and the lower temperature are given. And we are told that the gas used in the cycle is half a mole of a diatomic gas, with the gamma constant being 1.4. And then they ask us to calculate a number of things. So let's see if we can actually do this. All right. So this is problem 19. And we have a Carnot cycle. So let me just draw this to begin with. So it's a PV diagram. I'm usually quite bad at drawing Carnot cycles, but you have a much better figure in the book. So yeah. So this is an isotherm. This is an isotherm, and these are just adiabatic. So just to make sure, this is A, this is B, this is C, and this is D. And so they give us a number of things. They give us VA, VB, TH, and TL. So VA, VB, the higher temperature. So this will be the temperature over here, and TL will be the temperature, the lower isotherm, and number of moles is given. So N is given, and the gamma is given. So it's a diatomic gas. Its gamma is 1.4 for these temperature ranges. Okay. And so they're asking us to calculate a number of things. So the first thing they're asking is to calculate the pressures at A and B. So PA and PB. Right. Now the first thing that comes to your mind, because you know so many things about this point, is to try to use the ideal gas law, right? You know the number of moles, you know the temperature and the volume. It looks like you could just calculate these pressures. So PA, VA is just N, R, TA. So N is common, so I'm not going to put anything there. R is a constant, so that's obviously common. And we know VA, that's given. We know TA, this is the same as T high. And we know N, that's given. R is a constant we can look up, so we can just calculate the pressure. And something similar for the pressure at point B. This is going to an RTB. This is again just T high. It's on the same isotherm. And again, you know VA, you know N, you know TB, so you can just calculate PB. This is a straightforward application of the ideal gas law. Okay. For part B, the volumes at C and D, so VC and VD. Now these 2 points are connected to the 2 points about which we know everything by adiabatic expansion or contraction curves. So one thing that we can readily do is to write the adiabatic expansion over these curves, right? So the first one we can write PA VA to gamma is equal to PD VD to gamma, and for the second one we can write PB VB to gamma is PC VC to gamma. Okay? And we know everything on the left hand side, and in both equations. On the right hand side, however, in both equations we have 2 unknowns, so we need something else. Well, that something else is supposedly again the ideal gas law. That's going to be another relation between PD and VD, and also PC and VC. So for example, if you write for point D, if you write ideal gas law, we are going to have PD VD is equal to NR TD. Now TD is just T low. That is something given. So all of this right hand side is known. So this is 2 equations for 2 unknowns. For PD and VD, we have this equation, and also we have this equation. Right? In fact, if you divide them side by side, so then we can eliminate PD, and we would get something like VD to gamma minus 1. So I'm taking this, dividing out by this. PD is cancelled. I get VD to gamma minus 1. On the right hand side, I'm going to take PA VA to gamma divided by NR T low. Okay? And everything on the right hand side is actually known. So you can actually calculate the left hand side as well, because gamma is known. And you do something very similar for the point C using this equation, and then writing the ideal gas law for the point C. Again, you can divide side by side, obtain the volume at C, and once you know the volumes, you can use this equation, for example, to calculate the pressure. Okay? And then the ideal gas law for point C to calculate the pressure at point C. Oh no, they're just asking for the volume, so you just get the volume and you're done. Yeah. Okay. So for part C, what is the work done along the process AB? So at this point, we know everything about these points, right? And now we're going to look at the processes. So I'll just erase this. But keep in mind that we know the temperature, pressure, and volume at all the points A, B, C, and D. So for part C, what is the work done for along the process AB? So you can try out a number of things, but I'm not going to actually just fool around. The one thing you can do here is to write this as an integral of P dV. You go from A to B, and you can write the pressure in terms of volume and some other elements using the ideal gas law. So this is going to be from A to B and RT by V dV. Now, number of moles does not change. The R is a gas constant, that also does not change, obviously. And because the curve from A to B is an isotherm, the temperature is a constant. So I can take all of the numerator out, and I can write this as nRT high dV by V from A to B, and this comes to nRT logarithm of VB by VA. Okay. I'm sure this is done in some of the examples in the book over an isotherm. This is the work done. Okay. All right. So for part D, what do we do? What is the heat lost along process CD? So Q for CD. So it's from here to here. So we know how to calculate the work going from here to here. But these two are isotherms, and we are told that this is an ideal gas. So the internal energy depends only on the temperature. So the internal energy of these 2 points is the same. And we can write first law of thermodynamics and just get an expression for this Q. So delta E from C to D is going to be Q CD minus CD. Now you know how to calculate this. It's very similar to this one. It's the work done over an isotherm, and this is 0. Right, this is 0 because it's an isotherm. So QCD is just WCD, but that's just nRT. Now this time, so this was from A to B, this is T high. This is going to be T low, because now we are talking about this curve, the lower temperature, and it's going to be logarithm of VC by, VD by VC. Yeah, just in complete analogy with the previous part. So that will be the heat exchanged. I might be making errors on the signs because I'm not paying attention to the way it's formally this is stated, but I think you get the idea. So you should check if I'm actually using the correct definition, like heat given, heat taken, and so on and so forth. Maybe you should introduce a negative sign here. I'm not really sure. Yeah. All right. So for part E, let's see what they're asking. Calculate net work done for the whole cycle. So for the whole cycle, because we are coming back to our initial conditions, any state function, any change in any state function is going to be 0. In particular, the change in internal energy for the cycle has to be 0. Right? But this is, of course, the change, not change, but Q over the cycle minus the work done over the cycle. And so these two processes are adiabatic, so there is no heat transfer from going from B to C or from B to A. So if I write this, I can, first of all, from this I can write that W cycle, the work done over the whole cycle, is just the heat changed from the cycle. This is just conservation of energy, right? And this is going to be QAB plus QBC plus QCD plus QDC, right? And we actually calculated two of these. QAB, we calculated here, right? This is just because the internal energy going from A to B does not change either. This is just the work done over that. QCD, we have calculated here. And these two are 0, because these are over adiabatic curves, so these are 0. And this is just WAB, and this is just W. This is calculated already, so you can just write the numbers you get there and sum them up, and you're going to get the total work done for the whole cycle. Right? And part F is what's the efficiency of the cycle using the definition E equals W by Q high, and show that this is the same as given by equation of 3. So this is a show that thing. You'll just plug numbers in and see that the way the numbers you get both ways are actually one and the same. So there isn't anything additional there. Okay, so let's switch back to this. Now, so the second problem regarding Carnot cycle is, why would you expect the total entropy change in a Carnot cycle to be 0, and do a calculation to show that it is 0? Right? So you expect, so it's not very clear what they mean by the total entropy first of all, but let's just assume it's the total entropy change in the whole of universe, right? If what they mean is that this is it's going to be just for the gas itself, then it's trivial, because entropy is a state function. So for a whole cycle, any state function should come back to its initial value. So the change in anything in a state function is going to be 0. Right? Actually, I suspect this is what they're asking, because otherwise a calculation is impossible. But for a Carnot cycle, because every step is reversible, the total change in the entropy of the universe is also 0. Right? So this is something of a stronger statement, not just the gas itself, but for the universe it's going to be 0. It's possible that you do something non-reversible and come back to your initial state. Your entropy change for that particular portion of the universe is still going to be 0, but the total entropy of the universe will increase. For Carnot cycle, in both cases, the total entropy of the universe as well as the entropy of the gas, the change in the entropy of gas is just remains constant, is 0. So the entropy of the universe and the entropy of the gas remains constant. Okay, and you're to do a calculation that it is 0. Now you're just going to have to just take integrals of dq by t. So over two of these, going from A to D and B to C, this as we are going to actually exploit in a moment, it's adiabatic. dq is 0, so entropy change is 0. So you can do that, and you can calculate dq by t over these two isotherms. For an isotherm, the entropy change is simply just the heat divided by the temperature, the heat exchange divided by temperature, and you can just for example, by looking at the numbers we did for the previous question, you can just verify that this is the case, and you will need to just keep the symbols to show that this is correct in general, right? Just calculate dq by dt over these cycles. So you just need to calculate the entropy change from A to B and from C to D, and you're going to find that they're actually same but opposite in sign. Right? And the way to do those calculations, the way to write the expressions, is just what we have done for the previous problem, actually. So I'm not going to do this. Right? I'm not going to do the calculations again. Okay, so the next one is that the thermodynamic processes can be represented not only on PV and PT diagrams. Another useful one is a temperature entropy diagram. And draw a temperature entropy diagram for a Carnot cycle. What does the area within the curve represent? And so this is something we can do. This is actually different. So we generally do draw PV diagrams to show how things change, because we're very familiar with this. But because entropy is also a state function, that's also perfectly defined for any given gas, and we should be able to use that as an independent or dependent variable. And so this is problem 79. So I'm actually going to be drawing the Carnot cycle in the figure that I'm using for all of these questions. So we are going to have a TS diagram. Okay. to temperature and entropy. And let's just start at a point like this, the point A. Now I'm going from point A to point B. So in the figure, if you consult the figure, let me just reproduce it here. So I have an isotherm going from A to B and a diabatic curve, and then an isotherm and another diabatic curve, B, C, D. So these are isotherms, and this is a diabatic. Okay. So I go from A to B. Now, because this is an isotherm, it has to take place in a constant temperature, and because I'm taking heat in over this, I'm increasing my entropy. So I will just go parallel to my x-axis and reach point B. Now, as I go from B to C, this is an adiabatic expansion. There is no heat exchange, so the entropy does not change. Entropy remains constant, but I'm reaching a lower temperature, so I just go parallel to my t-axis and decrease the value, and I reach point C. Okay? And then, as I go from C to D, I'm going to be on an isotherm, so temperature is going to constant, so I will just move something like this. Now, how far I'll go along, I'm not really sure, but I will be moving parallel to the x-axis, the entropy axis. Now, as I go from D to A, I will be doing an adiabatic compression, and because it's adiabatic, the entropy is not going to change, so I will be approaching point A on a constant entropy line. Right, so this is going to be parallel to t-axis, this is going to be parallel to the s-axis, which means that they have to intersect at right angles at this point D. So what I get here is just a rectangle, something like this. Now the second part of the question is asking what does the area within the curve represent? So the area within the curve is, so let's just take a small part, okay, something like this, and let's say that we get the area by adding up all these little parts. Now what does this little part depict? So this is going to be, actually, let me just draw it this way. I will take a bigger part, the area under the upper curve, and I will subtract off the area under the lower curve, right? Because they're actually going in the opposite direction. One is adding things up, one is in increasing entropy direction, one is decreasing entropy direction. So their contribution, their integral, once I take them, is going to be opposite, right? If I write this as an integral. Now, what is that integral? This integral is just t ds, right? This rectangle, it is the base ds, and it is the height of temperature, right? So the blue one is going to be just the integral of this tds from this point to that point. The lower one, the red area, is going to be just integral of tds from this point to that point, right? And hence they have the opposite sign. So, but the overall area is just going to be this integral over a closed curve. So it's going to be something like this, tds. And I can actually go ahead and write ds as a differential. So ds is just dq by t. And so this is over some closed cycle, t dq by t. These, of course, cancel. And this is going to be the net heat that is exchanged over this cycle. The net heat that either enters or leaves our gas over this cycle. Right? Therefore, it will, of course, depend on whether you're going clockwise or counterclockwise. It's either going to be positive or negative. But in the end, we can just call this the net heat exchange with the system. All right, that's all I want to say.